Okay, ladies and gentlemen, this video is going to cover the second half of section 1-1 in your pre-calculus book. This is going to cover the domain of functions and how to deal with piecewise functions. Again, it's a review of Algebra 2. It's a little bit beefed up from what you learned in Algebra 2 most likely. So each function that we look at, what it has is a set of values that can be inputted to create the output. This set of values we know as the domain. So if we look at this graph and we're trying to figure out the domain of this graph, first of all, this graph has been truncated, but both endpoints are going off forever, both vertically and horizontally. So this piece is going to continue down and out forever. This piece is going to continue up and out forever. Okay? So what we have to think to ourselves when we're looking at domain is we have to think to ourselves, what x values are we allowed to plug into this function? In other words, if we look at this graph, are there any x values that do not have an assigned y value? So on letter A, since those extend indefinitely forever, there is not one x value that we can go to. Like say we go to 1, there is a y value associated with that. If we go to 0, there is a y value. If we go to 5, it'll be way the heck up here probably at the top, but it will exist. There will be a y value associated with that x. So what we would say here is that the domain of this function is all real numbers. But if you notice, the directions say that we have to write that in interval notation. So the way we write all real numbers in interval notation is we say every number between negative infinity and positive infinity. Now on the second one, letter B, you'll notice there's endpoints on the graph. What that tells us is that this function does not go on forever. So we're just asked, well, what x values can we plug into this function? So if you notice, the left endpoint, which is a closed point, is located at x equals negative 4, and the right endpoint is located at x equals 5. That means that this function exists from negative 4 to positive 5. And since both are closed circles, our domain would be negative 4 to positive 5 with square brackets. Here is a third example, letter C. If you notice here, this is actually two different pieces. So we've got a piece here, we'll call that piece 1. It's actually three different pieces. This piece here is piece 2, and this piece over here is piece 3. So for piece 1, that is running from negative 5 to negative 2. Both endpoints are closed, so our first point would be from negative 5 to negative 2 with closed endpoints. Then we use our AND symbol, and we write down the domain for the second piece, which runs from negative 1 to positive 3. So negative 1 is closed, positive 3 is open, so we use our parenthesis. And our third piece, which runs from x equals 3 to x equals 6. And 6 is closed. So that would be our domain for letter C. Okay. Now, when we're asked to find the domain algebraically, this is where we run into something that we don't necessarily remember that well from Algebra 2. There are only a couple of situations where the domain ends up being restricted, at least a couple that are common. The domain of a function is generally going to be all real numbers, except in just a couple of cases. Okay? So normally we would expect to have negative infinity to infinity for a function, except for certain cases. Okay? We have to look for cases where we could divide by 0, because that's undefined. We don't know how to do that. Okay, we can't do it. We're not allowed to divide by 0, and we're also not allowed to take the square root of a negative number. Okay, because that would result in an I. And I is not something that we can quantify. It's an imaginary number. So when we're asked to find the domain of each function, essentially what we're doing is we're trying to figure out what values we are not allowed to use. Okay? So in the case of a rational expression, what we're going to do is look at the denominator and think to ourselves, x squared minus 7x is not allowed to equal 0. So we would basically be solving the equation x squared minus 7x equals 0, except we're going to have a not equal sign in there. So that would be solved by factoring. Those two terms have a common factor of x, so we would pull out that GCF of x, which would give us x times the quantity x minus 7. Our zero factor theorem tells us that this means that x is not allowed to equal 0, and x minus 7 is not allowed to equal 0. Actually, we're going to use the and symbol there instead of the comma. Okay? So we are not allowed, repeat, not allowed to let x equal 0 or x equals negative 7. And we still have to write the domain in interval notation. So the way I always like to think about this is I like to think about a number line. On that number line, there's 0, there's 7, because we'd add 7, x is not allowed to equal 7. All right? I should probably clean this up a little bit. Let's clean that up a little bit. Okay, so here we would add 7 to each side, which means x is not allowed to equal. Okay, so I always like to think of this as a number line with 0 and 7 on it, because what that means is that when we're looking at what values are we allowed to use, we're not allowed to use those two values, meaning there are open circles at those two values. But every other number, every other real number could be part of our domain. So basically what we're trying to do here is write out the following inequality, okay, which is basically 3 different pieces. 1, 2, 3. That first piece is running from negative infinity to 0, not including 0. And every number between 0 and 7 is perfectly fine, not including 0 or 7. And every number greater than 7, so from 7 to infinity, is perfectly fine. So our domain would be negative infinity to 0, and 0 to 7, and 7 to infinity, not including 0 or 7. Okay, on the next one, we need to keep in mind that this is telling us that t minus 5 has to be positive. It has to be greater than or equal to 0. It cannot be negative, okay? It can't be negative. So what we do is we solve that inequality. T minus 5 is greater than or equal to 0, which is an easy inequality to solve. We just add 5 to each side and we've solved it. That tells us that t is greater than or equal to 5. So again, I always like to suggest that you think about what that would look like on the number line. That's a closed circle at 5 and shading to the right. So that means the interval would be a square bracket for 5 going to positive infinity, which is always a parenthesis. Now on letter C, they're trying to trick you. There is no fraction here. There is no negative square root issue here because there's no square root. If there's no division and there's no square root, chances are very good that the domain is just all real numbers. And in fact, for any quadratic equation, which is what this is, the domain is always all real numbers. So in interval notation, we would just say from negative infinity to positive infinity. Okay, so we're going to keep going. Here's some more examples. Here we go. So here, a little bit of a twist. Since this is in the denominator, it can't be negative. It also cannot be 0. Because if it's 0, then we have division by 0. So what we have to do is we have to take x minus 2, and that has to be greater than 0. It can't be equal to 0 either, like it would normally, because that would cause division by 0, which means x is greater than 2. Real simply put, there's 2, open circle, we're shading above. So that would be from 2 to infinity, both with parentheses. Here we have x squared minus 2x minus 8 underneath the square root, which means that has to be greater than or equal to 0. That is a factorable expression, x minus 4x plus 2. What that tells us is actually somewhat challenging. It tells us that the zeros of this function okay, we've got this thing to deal with. The zero factor theorem tells us where the zeros are. Okay, we should realize that the zeros of this function are the solutions of these two equations, x minus 4 equals 0, x plus 2 equals 0, which means that this function crosses at points 4 and negative 2. So 4 and negative 2, we have these closed circles, and we have some parabola that is passing through those points. So what's important is that we figure out whether we're shading, because this is a shading question, whether we're shading inside the parabola or if we're shading outside the parabola, because it's got to be one or the other. So what we do to figure that out is we simply test a point. For instance, the origin 0, 0. And we just plug that into the original expression, okay? And we see whether or not that is a true statement. So 0, 0 would mean f of x equals 0, okay? And we're looking to see whether or not, not the original expression, the domain expression. So we're plugging in 0 for x, and we're saying, okay, 0 squared minus 2 times 0 minus 8, and we're looking to see whether or not that is greater than or equal to 0. Okay, we're letting x equal 0. So that would be 0 minus 8, which is a false statement because negative 8 is not greater than 0. So this area is not shaded, which means we're shading outside that thing. In other words, our domain is going to be closed circles at negative 2 and 4, which is where that parabola is crossing, there and there, and we're going to shade out. So that would be negative infinity to negative 2 and 4 to infinity. And I just noticed that I didn't write that correctly because both 2 and negative 4 are included, which means we should have square brackets on both of those. That is by far the hardest example in our notes today. Our third example is another example of division, which means we cannot have division by 0. That tells us that x is not allowed to be 0, and 2x minus 3 is not allowed to be 0. A quick solve of that two-step equation, actually not equation, but equation, because we treat it like an equation, would yield the fraction 3/2, or 1.5. Okay, it's not allowed to equal 3/2. So again, think of a number line. There's 0, there's 3/2. Those are the only two numbers that we're not allowed to use for x. Every other number on that number line is fine. So when we write this out, we have three pieces: negative infinity to 0, 0 to, not a comma, and 0 to 3/2, and 3/2 to infinity. All right, that brings us to piecewise functions. A piecewise function is a function that is defined using two or more equations for different intervals of the domain. So what that's talking about is, depending on where you're graphing different stuff. So down here is a piecewise function h of x, When x is less than or equal to negative 1, we're using the expression 2x minus 3. When x is greater than negative 1 and less than 5, we're using the expression x squared plus 4. And when x is greater than or equal to 7, we're using the expression square root of x plus 2. So we're asked to evaluate this function at various places. So when we do that, it's all about finding the right piece using the domain of the pieces. We'll call this piece 1, this piece 2, and this piece 3, just so we can refer to them quickly. So when we're looking here, this first problem is saying x is negative 3. And we go over to the domain box and we find out where that would be. That would be here. X is less than or equal to negative 1. So this would be plugging into piece 1. So we would say h of negative 3 equals 2 times negative 3 minus 3, because we're plugging negative 3 in for x in the first piece. So h of negative 3 would be negative 6 minus 3, or h of negative 3 is negative 9. The second one, h of negative 1, is the same piece because less than or equal to negative 1 is the top piece. So this is also piece 1 because x is equal to negative 1. So that would be 2 times negative 1 minus 3. So h of negative 1 is negative 2 minus 3. H of negative 1 is negative 5. Okay, for 0, we ask ourselves again, if x is equal to 0, which piece is that? Well, that would be piece 2. So we'd say h of 0 is 0 squared plus 4, because now we're plugging into piece 2, which is x squared plus 4. So h of 0 would be 0 plus 4, or 4. Okay, the third one is h of 5. Now notice that this says less than 5. So when we go here, we're saying, okay, x is equal to 5. Well, that is not in any of our 3 domains. It's not there. It's not equal to 5. So this is undefined. If the x value is not in the domain, it is not defined for that function. Finally, for h equals 9, that is h of 9 when x equals 9, that is piece 3. So we would say h of 9 is equal to the square root of 9 plus 2. So h of 9 is the square root of 11. Okay, that does it for section 1-1. Thank you for your attention.